Briefly, briefly just going through a few points which I've already discussed a number of times. In our earlier, earlier study of strength of material, what we have discussed about the stress is it is the resisting force per unit area when while it is opposing the externally applied load over a say cantilever beam over a prismatic bar along its longitudinal axis. And we think this stress is the resisting force per unit area of the cross section, and we are thinking that this resistive force is same or equal everywhere in the cross section itself. But in actual practice, we have noticed in that this assumption is not right, because even for a single cross sectional area, all the forces are not exactly equal. They may vary from point to point. They may be make bigger, they may be lesser than the average mean. And in order to know the maximum force for our design purpose, we have to calculate what is the maximum force exists over a particular section, which means we have to find out what is the principal stress and what is the plane over which this stress is acting. So, in order to do so, we have in order to do so, we have taken the help of vector calculus. We far, so far we have taken into account only the values of our stress and strain and distance, length, etc. But now we are thinking and we are finding out what are the vectors and what is the scalars exactly it is. We have discussed that velocity, force, this type of, the items are known as vectors because it has uh, value as well as a definite direction where the length, width, etc., length or other dimensions are scalars, length, temperature, etc. These are all scalars because they have the only the value, not the not the direction itself. They are same in all directions. That as we are thinking that the for each cross section, the force of the or force for unit area or the stress is uh, different from point to point, and there may be different from direction to direction. So we are using the force as well as the stress as a vector quantity. Vector quantity means we are using the same value. We are not changing the value, but we are taking into account the application of its direction of line of action. Now, let us go through a let us go through consider a body which is occupying a certain area of space in a three-dimensional coordinate system, that is O, X, and O, X, Y, and Z. And as per this figure, you see this body is subject to a number of external forces. This like F1, F2, F3, and R1, R2, R3, and P. These external forces F1, F2, F3 are concentrated or single forces, and the volume, the force P is as distributed forces, and the reactions the R1, R2, and R3 are the reaction of these forces of this F1, F2, F3, P, all these forces reaction, because this bar, whatever it may be, it's supposed to be supported by some supports in some or in length. At least more than one support is required. So we are using the forces carried by the supports like R1, R2, R3, which is also distributed, shown as distributed in nature, and it is placed in different places of the body itself. Now, these are the, in general, all these bodies will subject to two type of forces here as per our definition. What is body forces? One is surface forces. These forces which I have shown you here, F1, F2, F3, etc. These are all surface forces. And what are the body forces here? The body forces acts on each volume elements of the body. Example of which type of force is I'm just telling you. are the gravitational forces, inertia forces, magnetic forces. This also acts on any type of prismatic, any type of engineering material or any type of prismatic bar, even to us. The surface forces acts on what the area of the body, and where the area considered lies exactly on the boundary of the body itself. Surface forces distribution is sometimes you can say that the surface traction. So let P is the point on the body, and let's explicitly assume that under the action of body forces and surface forces, the body is in equilibrium. This is one of the most important thing. Whatever may be the force act, body force or simple force, force may be concentrated, may be distributed, may be reactive, but they are keeping the body in an equilibrium itself. Now, let us let P be a point on the inside of the body with coordinates exercised in the let the body itself is cut into two pieces. And what he will say, and we consider the figure as the bodies are equal to one of them is C and one of them is D, and we consider them are as we consider the body is perfectly equilibrium, we can apply the construction of free body diagram over C and D. It from the theory of superposition in your strength of material, I hope you can remember that we have separated imaginarily different bodies into different parts, and the whole body is supposed to be in equilibrium under the action of all different forces acting over it, and individual parts which we have separated also under equilibrium with each other, because the one body, if you separate the body from its rest, actually it is the imaginary separation. So you have to understand that due to this separation, to maintain the equilibrium of the body itself, we have to apply certain imaginary forces acting over it. Here you see the body C and body D, they are separated, but they are in equilibrium to equilibrium among themselves. And so the external forces like here, say R3, R1, R3, F1, P, F2, delta P, F2, etc. These are the external forces are being balanced by an imaginary forces delta T1, which is a vector. That's why it is written like this. Similarly, the body part D, which is subject to the external forces, say R, F2, R1, etc., etc., and it is also all these things, the external actual forces are being balanced, or that body D is kept in equilibrium by another imaginary force delta T. That is the same as equal to delta T, because they are supporting each other, they are cancelling each other, but they are acting opposite to each other. Now, let us consider mm, let us consider the part D. There we are looking at a sectional area, a small area, infinitesimal area surrounding the point P itself. In part C, we have the same area of surrounding point P dash by an amount, and the area is delta A dash itself. These two areas are distinguished by their outer their normals n dash and n. Now, actually, it is n dash, n and n dash itself, and this is as a vector, as it is shown as a vector equal to. So this is there is a one here, one here. The action of the point C on A dash area will be represented by the force vector itself, and delta T dash here. We are seeing that the action of the external force delta T dash is acting over the area A dash, and the action of the part D here, from here we are finding this force vector delta at A dash at P dash can be represented for force vector delta D dash. So both the here part A area is A delta A dash, part B area is delta, part D area is delta A. and force delta A dash is acting over this part A, part P, and same is the same force acting over the part D itself. So what we are doing here, let us make a ratio. As we know that we are going to calculate the stresses in different points. The stresses is the force divided by the cross-sectional area. Here, let us do like this. The moment of the forces acting on the area without any point sets the limit. With vanishes in the limit. There are any other point because they are in equilibrium, all the moments will be required. The limiting vector is written as delta t divided by delta A is a limit A tends to 0. Means delta A tends to 0, almost infinitely equal to 0, then this ratio will become dt dash by d or simply t dash. It is not the force but the stress acting on the infinitely or differential element delta A, which is the stress itself. Similarly, at the point P, dash on the part D, and as delta tends to 0, it will be represented by the vector, same vector, theta t dash by dash itself. This vector t and t dash are called the stress vectors because they are defined as per our definition, the force multiplied force divided by the cross-sectional area itself. Whatever may be the small the area is, this is the area is there. So this is the cross-section stress vectors. Just 1 second. Okay. 3. Now, that represents, so these two T and T dash represents the force per unit area and and on the planes with outer drawn normals N dash and H dash. At P dash, P and P dash, and with the area P and P dash, and with the outer drawn normal as N dash and N dash itself. The planes here was actually P, we have got two planes here. One is P and one is another P, which is on D, and one is P dash, which is on C. And each plane can be defined by the normal which is acting over it. So here having the normals N dash and N and N dash here, or respectively for the area P and P dash. Now the stress vector representing the action of C and D at P. So they are equal in magnitude and opposite direction to stress vector T dash. Just I have told you like this. So T dash is equal to T dash itself. Next, if we take the irrigation, again we are making the our body under our consideration is covered by different plane 2 2. We have cut it initially by 1 1 plane. Now we are making it 2 2. Now here the outer drawn normal N2 and passing through the same point P, and then the stress vector is represented by T2 shown in the value cell. So T2 is equal to limit delta T to the delta T divided by delta A dash, and it is represented t to the power 2 because the plane is different, not the original plane itself. The stress vector T1, which was acting on the plane number 1 at point P with outer dot normal n dash, will be different from stress vector T2, which is acting on the same point P but on a plane but at a different normal. So what we find decides here, the stress of the point depends not only on the location of the point itself, but also on the plane passing through the point. For any point, there can be thousand or lakhs of planes can pass for any point. So the we are saying that there these planes, the normal acting over the planes are different, and the forces acting over the planes and the stresses acting over the planes are different from each other, although they are acting on the same area. So thus we are coming into the conclusion of that the force depends on the point, and the force or the stress depends on a particular point, not on the area, and the area and the normal over which it is acting, it can be different from different or the same points itself. And the point n, the normal n, which is passing through the point, is can be defined also in another way. The direction cosines nx, ny, nz, which is the cosine of the this normal with x-axis, y-axis, and z-axis itself respectively. Now let us discuss what is the state of stress at a point. Say an infinite number of space planes can be drawn through a point. Just this is sometimes a bit difficult to assume this concept of stress, but if you follow up, I think it will be clear to you. This subject definitely a bit difficult, but it is interesting and challenging also. Let us do as quick as possible. Since an infinite number of planes can be drawn through a point, we can get an infinite number of stress vectors acting at a given point. So what I am meaning, say a body in space, in three-dimensional space, any point you've selected over the body, maybe in the surface, maybe in the region, but actually we select the points in the surface of the body, not the central inside of the body itself. But for this point, infinite number of stress vectors is acting because each vector is characterized or defined by the plane on which it is acting. The totality of all stress vector acting on every possible plane passing through this point is defined to be the state of stress at that point, which means a point over which a force is acting, and if we go through each infinite number of stress vector can be act on a given point, because on one point we can have infinite number of planes through that point, and each plane have a unique normal, and each plane can have a stress vector acting over it. So each stress vector is characterized by the plane over which is acting, or the normal what is acting over that plane itself. Its totality means all stress vector acting on every possible plane is passing through that point is defined as the state of stress at that point. This knowledge, it is this knowledge of stress, if it is important that the designer to know the critical plane and the respective critical stress. Whatever you are discussing so far, we are interested to know what is the critical plane, and out of so many infinite number of planes, and what is the critical stress acting over that critical plane itself. If the stress Vectors acting on this mutually perpendicular plane passing through the points are known. We can simply divide by stress vector acting on any arbitrary plane on that point. Let us see how can we make it. Now, let us go through what is the normal and shear stress component. Just 1 second. Let T, it is a vector with a sign n, but it is acting over along the normal of certain points, normal of a plane on certain points. But let us examine that even. T is the resultant stresses, resultant stress vector at a point P acting on a plane whose outer drawn normal is n. At a plane with this particular stress, force per unit area acting along on a plane whose outer drawn element is normal, outer drawn element normal to it is not n. So any plane should have a normal. It must have. So here, this stress T is acting on the plane who has a normal equal to n, and other is perpendicular to n. So stress is acting along the normal, and another stress is acting perpendicular to the normal. Component parallel to the normal is called normal stresses, and the component denoted by sigma, as we already knows, and component parallel uh, normal to n is known as tangential stress or shear stress. Not parallel, but normal to it is tangential or tangential shear stress component and defined by tau. As n we are using because we know that the normal of this particular plane is n. So as this one of the resultant of this force is acting, resultant of the force T, it's one component acting normal to the acting along the normal n is represented by sigma, and another problem is another component acting normal to this normal, which is called tau or shear stress component. So we have the relation T resultant is equal to sigma square plus sigma square minus tensile stress whole square plus tau stress whole square. It is all these are represented given in vector sign because it is acting on the acting on this resultant stress T. This is stress, not force. Is acting on a plane whose normal is n. That is the definition of that plane. And the sigma is acting sigma, its component sigma acting along this normal, whose normal is defined as n, and tau acting perpendicular to the normal, that normal which is defined by n itself. Now, T to the power n or T is the magnitude of the resultant stress. Stress vector can also be resolved in three parallel planes, three components parallel to x, y, z. We can have the we can had we can resolve the resultant as normal to normal and along the normal of this plane, like sigma square tau square. At the same time, we can this stress vector T can also be resolved in three components parallel to x, y, z axis itself. These components of the resultant vector is denoted by Tx to the power Tx, Ty, Tz. All are denoted by n as a vector because its resultant T is acting on a plane whose normal is n. So that's why everywhere this n is written here. T square is equal to Tx square plus Ty square plus Tz square. Resultant will be The square of the resultant will be square of the individual component and just adding them together. Now rectangular state components. Now let us consider a body B. This is like this. Cut out to be cut by a plane parallel to YZ plane. What is YZ plane? This plane and this plane itself is YZ plane. We have a we have a plane which is parallel to the plane which cut our body under consideration, and this plane which is cutting our body is parallel to the plane YZ. The normal to this plane is parallel to it must be parallel to the x-axis like this. Normal to this plane N is must be parallel to x-axis because the it is cut parallel to YZ. To anything, any line normal to it will be along the x-axis or along OX, parallel to OX. The result of the stress vector at P acting here like T will be Tx. Here on this plane will be Tx. Thus, this plane is defined as x plane. We have just written this parallel to x-axis, and this plane is defined y. This one normal to this plane is parallel to x-axis, and thus the plane is called x plane. So the resultant stress vector at P acting on this will be x to the power x, as it is acting along x-axis. This vector can be resolved into three components parallel to x, y, z axis. The component parallel to x-axis being normal to that plane will be denoted by sigma x parallel to x-axis, sigma x, but we are not writing sigma to the power x, but we are here writing normal sigma x, as we are using x as a suffix, but it is still a vector itself. Just for our similarity, for our convenience, we made it sigma with the suffix x. The component parallel to the y and z axis are shear stress components because they are denoted by tau xy and tau xz. Here on this plane, the components acting like this should be parallel to yz, and coupling acting like this component parallel to acting is one component acting x like this, which is parallel to z-axis, another component acting vertically along the x-axis itself and along the y-axis itself. They are all, as it is acting parallel to this plane, it is called shear forces. So we have one normal forces along the x-axis, one shear forces along y-axis, one of the shear forces along z-axis itself. Here always we are writing tau xy, tau suffix xy and tau suffix xz, and not tau suffix yx or tau suffix xz itself. Now, in the above description, the first suffix x denotes the plane on which the stress are acting, and the subscribes y or z indicates the direction of the component itself. So, if there is tau xy is the stress component in x plane, which you have just said what is x plane, we have described, and it is acting in y direction because this particular shear stress is acting along the x plane, not normal to it. So we are writing the first suffix as x and second suffix as y because y is acting along y-axis direction of y-axis itself. Similarly, Zx tau Zx is the shear components, and where in x plane, which is acting along z axis. So we got one shear plane acting along y axis, y direction, another is acting along z direction itself. The To measure this consistency, we want to have noted that normal trace we can write that x axis, xx, but here we don't write like this. Normal trace we can write as tau x axis, but we don't. But this is the stress is explained x plane acting in a direction of x axis. But to distinguish the normal and shear stress, we always denotate the normal stress by tau and shear stress by normal stress by tau, sigma, and shear stress by tau itself. The plane on which the x plane is normal is called x plane, and so always x plane is normal, the plane is called x plane. At any point P, we can have three mutually perpendicular planes x, y, and z. The normal shear stress on these planes can be sigma x, tau x, y. Sigma x means normal x acting along the x axis, and tau xy, it is on the x plane acting along y axis. Tau yz, it is on y plane acting along, it is along in y plane acting along z axis like this. Sigma tau y on x plane, and sigma y on y plane, and sigma z on z plane itself. So here x plane normal place is x, sigma y, and sigma z, tau x, sigma y, sigma x on the x plane itself, and along y, y plane itself along z, and z plane itself along x itself. Like this, the components are showing acting on small rectangular elements surrounding the point P itself. Hmm. What we are having here, one should observe that the three, we have one three-dimensional coordinate system x, y, z, etc., and we have one cube here. The three inside faces of the cube, we have this face is visible to us, this face is visible to us, and this face is visible to us. And other three faces, cube has total six faces, you know very well. This one, and this one, and this one are not visible to us. If the cube is, if you place the cube like this way. But three visible faces of the rectangular element have their outward drawn normal along positive x, y, and z axis respectively. Here, this visible face, this is visible, its normal is acting along x-axis, and this is the visible place, its normal acting along z-axis. This is another visible place whose normal acting along y-axis itself. Now, consequently, the positive stress component of these faces will also be directed along the positive axis. So we know from if this is the origin O, from O rightwards is the positive direction of x-axis, O towards us is the negative positive direction of z-axis, and O above us, above direction is the positive direction of y-axis. So what we know, the positive stress component on these faces will have therefore directed normal to the negative y-axis itself. So all these forces here is acting along the positive direction of x-axis. Next comes the invisible or hidden faces like this one, and this one. Here, this normal is acting along y-axis but to the negative direction of y-axis, and this normal acting along x-axis but towards negative direction of x-axis, and this is along z. This normal here inside it, it is a jet. It is although this one, it is uh, it is not. I could not write it properly. There is a z normal here in the z in the invisible side. It is acting along z, but towards the negative direction of z-axis itself. Hence, the positive stress components in these spaces, that is sigma y, tau y, tau j, yj, is directed respectively along the negative y, x, and z axis itself. So if you have this thing, so what we have here is not clearly very clear here itself. If the tau is acting in the z, positive z axis, this is positive here. This tau here acting, the positive x is there, but because acting on x plane, and it is x is there acting on level, it is acting along the positive direction of z axis. So that is the positive direction, and so everywhere you have to find out which axis, which way it is acting, is positive or negative direction, and you have to understand this like this. So what we find here, the visible planes, all these three forces are acting, and the tensile and shear stress are acting in the positive direction of their respective coordinate axis itself. Now let us go through a stress component on the ideal plane. What is this? We have again that three-dimensional axis x, y, z. We have stated that a knowledge of stress component acting on three mutually perpendicular planes acting through a point will enable one to determine the stress component acting on any plane passing through that point. If we know the stress component of a three mutually perpendicular planes like this one, this one, this one, and well, these particular planes are mutually perpendicular passing through a point, then determine the stress component acting on any plane passing through that point itself. So if we know the stresses value here, here, and here, which is shown here, sigma x, sigma y, tau x, tau a, etc., and any plane, if we want to can pass through this point P itself, we can safely calculate on this point. Now let the three mutually perpendicular planes be x, y, and z planes. So, and let the arbitrary plane is identified by the outward drawn normals on these directions, on normals n, whose direction cosines are nx, ny, and nz. So what we get? Three mutually perpendicular planes, this one, and this one. That can be x plane, that can be y plane, and that can be z plane itself. And let the arbitrary plane be identified by the outward drawn normals n. Means all the planes is supposed to be known by their normal n, and whose direction cosines, means if you have a normal n here like this, if you have a normal n here like this, then its